Hi everyone, I'm Louis Deheb, and in this workshop I'm going to present our work entitled an SE3-based formulation of the shape servoing problem. A general approach to solve manipulation tasks is shape servoing, also called shape control. The goal of shape servoing is to provide commands to a robotic manipulator so that it deforms a deformable object autonomously to give it a desired shape. In the literature, there are model-based and model-free approaches. Model-free ones operate in closed loop. The desired shape is given as input and is compared to the current shape of the object. With this, we obtain a shape error that a control law transforms into robot commands. Once these commands are executed, we obtain a new shape of the object from which we extract features of interest to close the loop. Different solutions have been developed for this, but a very interesting one is to use position of points in space, since this provides a direct way to define the target from the task objective. So in this approach, that I will call position-based servoing, the features in the control loop are defined by the three components of points on the object. We note them y and their desired position yd. Moreover, independent grippers grasp the object rigidly and their pose is noted z. Then, if the system is quasi-static, we can linearize around the current configuration to obtain a relation where a Jacobian relates gripper motions to feature motions. This matrix is called the shape Jacobian, and estimating it correctly is a key ingredient of the approach. To estimate J, what we have at disposal is an history of pairs delta z and delta y. Several techniques can be used, and in this work, we choose to illustrate with the broaden update rule, but our method, we emphasize that it is not tied to this rule. What is important to note here is that delta y and delta z used in the update are defined with respect to an inertial frame, so that the shape Jacobian depends on its choice and is not independent on rigid body rotations. Once J has been estimated, we can use its pseudo-inverse and the shape error to obtain gripper commands. Usually, this error incorporates only the position error of the feature points. In our SE3-based approach, instead of using points as features, we propose to use mobile frames defined from the surface of the deformable object. The goal is now to control the grippers such that the feature frames reach a desired pose. This pose incorporates the position of the frame, but also a rotation matrix defining its orientation. HP is the current feature frame, and HD is the desired one. Now, since the shape Jacobian relates motion of frames, we need to redefine the broaden rule. The key difference is that now we use relative transformations between the successive feature frames, and we use the logarithmic map to obtain a vector that we can use in the broaden rule. We do the same for the gripper motions, and in the end, all the variables used in the broaden rule are now coordinate independent and insensitive to rigid body motions, so that it will also be the case of J. Very importantly, we need also to redefine the shape error, so we use the relative transformation between frames HP and HD and the log map. Compared to the traditional approach, the error incorporates also rotation information. Again, we simply invert the model to obtain gripper motions, and we update them with either position or velocity control. To illustrate the results, we have made several experiments in the simulator PyBullet. The controller has no access to the object model, and we initialize the Jacobian with small perturbations and finite differences. In the traditional approach, called here position-based servoing, we use 3 points shown in green here, and we use the same points to build the frame HP in our new approach. For small deformations, we observe that both methods work. However, the advantage of SE3-based servoing is more visible for high deformation tasks. Here, coupling position and rotation in the error avoids twists because it deteriorates the rotational part of the error. The trajectory we obtain is smoother and more straightforward. In contrast, for these two tasks, the traditional approach failed. Finally, when we subject the beam to rigid body rotation, we observe that in position servoing, the components of the Jacobian vary non-linearly, while in our approach it remains constant, which should be the case, since the shape Jacobian should only capture shape variations. Finally, I would like to thank the ERDF that supports this research through the ICRA project. This is an Interreg project in the region Meuse-Rhin that gathers partners from several countries to promote the development of composites in the region. To conclude, I would like to highlight that our approach is not tied at all to the broaden rule, nor to the controller used here, so our method could be easily extended to other frameworks. Thanks a lot for your attention, and please do not hesitate if you have any questions.